Hi, my name is Sean Madigan, and my talk is titled Socioeconomic Status and Land Cover as Predictors of the Urban Heat Island Effect in Tempe, Arizona. So what is an urban heat island? So materials in urban environments absorb more radiation from the sun and emit more heat as well, warming urban areas more than nearby rural areas. So you can see, say, the city over here would absorb more sunlight and emit more heat than, say, this grove of trees. This is called the urban heat island effect. The primary cause of this effect is the materials used in urban construction, which tend to absorb more sunlight. So land surface temperature is the temperature of ground surfaces exposed to sunlight, and it is an important indicator of the intensity of the urban heat island effect, as land surface temperature would be higher in areas that are urban than in areas that are grassy or covered with trees. Urban heat islands can cause increased health risks from extreme heat conditions in cities. There is also evidence that urban heat islands tend to affect areas of lower socioeconomic status more than wealthier areas. Wealthier neighborhoods tend to have greater tree coverage and more grassy lawns, both of which reduce the urban heat island effect. One of the common methods, therefore, of mitigating urban heat island effects is to increase tree cover in an area. Planting trees will cause a decrease in land surface temperature and a decrease in this urban heat island effect. But planting trees is often not equitable. Poor communities tend to fall further behind as cities develop due to slower planting of trees. So for my project, I was focusing within the Phoenix metropolitan area, located in central Arizona. It is in the Sonoran Desert. It's one of the hottest and driest major metropolitan areas in the United States. In the Phoenix metropolitan area, extreme heat is a significant public health risk, especially within poorer communities where preventative resources, effective cooling options as well, are not as readily available. The Phoenix metropolitan area has grown very dramatically since Arizona became a state over 100 years ago. So 100 years ago, or just over, in 1912, you can barely see the urban area, a tiny gray spot underneath where Phoenix is located within the Phoenix metropolitan area. And since then, that gray spot has grown dramatically to now where the Phoenix metropolitan area is very large and has a population over 4 million. Since 1995, that population has actually doubled. For my project, I am focusing in particular on Tempe, Arizona. So Tempe is southeast of the city of Phoenix. It is just over 100 square kilometers in area, and it has a population over 180,000. That makes it the highest population density city in the Phoenix metropolitan area. It's home to Arizona State University and has a large college student population. The Tempe Urban Forestry Master Plan set a goal of 25% tree cover within the city by the year 2040. So the three goals of this project are, well, first, to classify land cover in Tempe and assess current progress towards that goal of 25% tree cover. Second, to measure land surface temperature and contrast land surface temperature with land cover to see the effect of different surfaces on temperature. And third, to evaluate the relationship between socioeconomic status, land cover, and land surface temperature in Tempe. For my project, the data I used, I had two main data sources. The first was Landsat 8 satellite imagery. So this satellite imagery is available roughly twice a month. So I selected data from throughout the year 2020 and looked for data that was a hot day that had little to no cloud cover, and so a clear day. And the date I chose was July 7th, 2020. The high that day was 110 degrees Fahrenheit, or 43 degrees Celsius, and it was a clear day. So the first step was to process the satellite imagery to remove atmospheric haze. What you can see here is satellite imagery from July 7th, 2020. It has been processed to remove atmospheric haze. This is a true color image showing just 3 of the bands from the Landsat 8 imagery. So just red, green, and blue in this data. In addition to the Landsat 8 imagery, I also used 2019 Tiger line shapefiles and 2019 American Community Survey 5-year estimate data. This is from the US Census Bureau and was used to estimate and evaluate socioeconomic status throughout Tempe. That data is organized by census tract. Tempe has 37 census tracts, so these are the units of measurement for socioeconomic status, these areas here. For the classification, this was the first step, was to classify land cover in Tempe. An initial unsupervised classification was used to find 5 classes of land cover within Tempe. Tempe pixels were assessed as either urban, tree, bare ground, grass, or water. After that initial unsupervised classification, 2 additional unsupervised classifications were completed for a total of 3, and 2 supervised classifications were completed as well to try and find the most accurate classification. To assess classification accuracy, I acquired 150 ground truth validation pixels for each of these 5 classifications, and then went through and looked at each pixel and decided whether it was urban, tree, bare ground, grass, or water. That was a total of 750 pixels that I was going through and identifying. That's a lot. The reason why there were so many pixels is because, well, so let's take a look really quickly. This is NAPE imagery, not Landsat imagery. This is a really nice high spatial resolution image. Each pixel in this image is 0.6 meters by 0.6 meters, or about 2 feet by 2 feet. On the ground is the pixel size. One Landsat 8 pixel is 30 meters by 30 meters, this white square. So instead of having all of the detail that we can see in here, each pixel was actually showing this much data on the ground. And so the job of the classification process, and also me when I was going through and doing this ground truth validation, was to look at a pixel and decide if it was an urban pixel, tree, bare ground, grass, or water. And I can't choose multiple. I have to just choose one for each pixel. That's a pretty difficult process. So the second part was the land surface temperature calculation that was using the Landsat 8 data and the radiative transfer equation method to solve for land surface temperature. The primary data used for this was band 10, which is thermal infrared. It went through a top of atmosphere radiance conversion to solve for land surface temperature. In addition, bands 4 and 5, that's red and near infrared, went through a surface reflectance correction. Then they were calculated for normalized difference vegetation index, and that was used to estimate land surface emissivity, which was the second piece of data used in the radiative transfer equation. The final piece were some environmental parameters that were pulled from a historical weather record website. For the third part, the regression, I was predicting mean land surface temperature using ordinary least squares regression. I began with an exploratory regression with 8 variables to predict mean land surface temperature. There were 3 socioeconomic status indicators: mean household income, percent of the population in college, and percent of the population in poverty, and 5 land cover percentages: urban, tree, bare ground, grass, and water. And each one of those was just the percent of the census tract covered by each of those types of land cover. The best fitting model was then analyzed for spatial effects, and the final model was either ordinary least squares, spatial error, or a spatial lag model as appropriate based on spatial effects. So looking at the classification first, what we can see is that most of Tempe is urban. There are decent patches of tree cover in northern central Tempe and in southeast Tempe. There are patches of grass throughout, which are generally parks. Some splotches of bare ground, especially in northern Tempe. And then most of the water in Tempe is in North Tempe, Tempe Town Lake. The overall accuracy of this model was 78%. Challenges were urban and bare ground, which are hard to tell apart sometimes. Tree and grass are both types of vegetation and are difficult to differentiate. And urban and tree, because tree cover pixels usually aren't fully tree cover. That would be 30 meters by 30 meters of pure tree cover. Really what it is there's a few trees in the pixel, and the rest of it might be an urban environment. So that was really hard to tell that apart. Land cover by class. So 65% was classified as urban, 23% by tree, although I'll comment more on that shortly, 8% bare ground, 3% grass, and 1% water. Looking at the land surface temperature, you can see that the effect is pretty clear here. So in white, you have water. In purple, you have usually grassy areas. So green to cyan, you have the tree cover areas, and then red and orange, you see a lot of urban and bare ground. So that relationship between land surface temperature and class is pretty apparent from the land surface temperature. For the regression analysis, the dependent variable was mean land surface temperature, which we can see here. Areas with low land surface temperature, north central Tempe, southeast Tempe, and then higher land surface temperature, especially along the western side of Tempe, and then running through the center were hotter areas. There were 5 variables that were used in the best fitting model from exploratory regression. 2 of those variables were socioeconomic status variables. The first was mean household income. You can see high mean household income in southeast Tempe and South Tempe, and generally you find that those are areas with lower mean land surface temperature. And then percent of the population in college, which tended to be high right around ASU rather predictably, and that was an area that had lower mean land surface temperature as well. There were also 3 land cover variables that were predictors of mean land surface temperature. Urban was 1. Higher urban land use percent was associated with higher mean land surface temperature. Grass was a second one. Higher grass percent was associated with lower mean land surface temperature. And the last variable was water percent. So higher water cover was associated with lower land surface temperature. So the final model actually had 6 explanatory variables. I just showed you 5 of them. So there were 4 negative relationships. Mean household income, percent in college were the 2 socioeconomic status indicators that had negative relationships. As those increased, the land surface temperature decreased. In addition, percent grass cover and percent water cover also had negative relationships. As the grass cover and water cover increased, so did the land surface temperature. 2 positive relationships. As urban land use increased, the land surface temperature also increased. And the last one was a spatial lag effect. There were spatial effects in this model. And what that's basically suggesting is that as the land surface temperature of a census tract, say this census tract here, increased, the land surface temperature of surrounding census tracts was also higher as well. So there was a relationship based on spatial effects. So in conclusion, the percent tree cover was pretty unclear ultimately. I got 23%, which is really close to that that ideal 25% goal by 2040. That they're not 20 years ahead. Really what's going on there is that a pixel that was classified as tree cover often had a lot of other things in it as well. The tree cover was partial, and that caused it to be considered tree cover. However, it was very clear that land cover does influence urban heat. So the urban and the bare ground land classes were much hotter in general than grass, water, and tree cover. Tree cover was a little bit harder to see. It wasn't one of the variables. Ultimately, the greatest effect of tree cover is underneath the trees rather than on top of the trees, which is what was being measured. And finally, low socioeconomic status areas along the western edge of Tempe and then through central Tempe were more at risk. They had higher land surface temperature than areas to the north, which had higher socioeconomic status in terms of it was full of college students, so generally higher education. And then southeast Tempe as well had lower land surface temperature, and those were areas that were much higher income. And both of those areas were less at risk, whereas throughout central and western Tempe was greater risk. So thank you very much, and that is my talk.